Hello everyone, and welcome to this Introduction to FESafe webinar. Today's webinar is an introduction to FESafe. We will be looking at the importance of using sophisticated fatigue software tools to save time, money, and materials, and ensure the accuracy of our durability calculations. We will examine the unique benefits and capabilities of FESafe for FEA fatigue analysis and why all fatigue software is not the same. Today's presentation is structured around 5 commonly asked questions. It all starts with the simple but fundamental question, why do fatigue analysis? Fatigue analysis is important because fatigue failures are expensive. In the automotive industry, prototypes account for around 40% of development costs, and a component failing before its optimum fatigue life can mean expensive product launch delays, product recalls, warranty claims, and legal liability. Therefore, fatigue analysis plays a key role in the right first-time design process. Simulation is a fraction of the cost and time taken for physical testing in the prototype phase. Optimizing designs to reduce the material in a typical car by 1% is said to pay back $60 million over the product lifetime of the model, for instance. Fatigue failures are more than just financially expensive. In the 1950s, the 3 aircraft lost by the manufacturer Cummins de Havilland due to fatigue failures resulted in devastating loss of life. And Cummins lost the industry lead to Boeing, and it took Europe another 50 years to gain parity with the US in sales of passenger aircraft with the launch of Airbus. So we know what happens if you don't do fatigue analysis. Let's look at what happens if you do. The cost benefits can be significant, and real competitive advantage can be gained. This is a virtual design validation project by Jaguar Land Rover using FESafe TurboLife to look at the high temperature creep and fatigue interaction for the design and optimization of their exhaust manifolds. The project enabled the engineering department to identify an alternative, cheaper material, and FESafe enabled the engineer to create a near-optimal design early on in the design process. As a direct result of this project, the company has reduced the number of prototype tests they have to do on exhaust manifolds, leading to huge cost and timescale benefits. It's very clear why we need to undertake fatigue analysis, so let's take a look at why you need intelligent fatigue analysis software to do this fatigue analysis calculation. First of all, let's identify what we mean by intelligent fatigue analysis. This is a design workflow involving fatigue analysis. A designer passes his or her design to an analyst to do the FEA analysis. FESafe then takes the stress and possibly the strain or the temperature from the FEA software and combines it with loading histories and materials data and gives you a fatigue life prediction which is seen as a contour plot in your FEA software or viewer. And you do your redesign based on those results, or you can sign off with just one validation test once the design is complete. You can see all the supported input and output formats for FESafe can interface to on this slide. As you see, we support all of the major FEA software packages. Why do we need intelligent fatigue software? Firstly, because we can't rely on physical testing alone. It's a slow and open-ended process where it's impossible to consider all conditions. In the previous example, Jaguar put the cost of a single engine test around 30,000 British pounds. Jaguar's aim of reducing the number of tests from 5 to 1 will not only save 120,000 British pounds on 4 unnecessary tests, but it will also have a benefit of reducing emissions due to using less fuel during the engine testing. Of course, physical testing should be done, but it needs to be done only once and at the end of the design process when you're 99% sure of your design. Secondly, because we need to get the fatigue analysis right. Many companies use advanced finite element analysis to calculate design stresses, but the fatigue analysis is often still done by manually picking stress points from a spreadsheet. These types of methods and hand calculations are inadequate for anything but the simplest fatigue scenarios. With these methods, too much is left to user interpretation. It is too easy to miss a failure location by focusing on the wrong selection of a model, and it's again impossible to consider all conditions, alternatives, and variables. This is a drive shaft assembly, and that came from a case study done by Dana Automotive. It shows the case for why we need intelligent fatigue software. On this drive shaft component, the crack did not start from the point of maximum stress, and the results were confirmed by testing. So, the more complex loading, the less correlation there is between stress plots and life plots, and therefore it is dangerous to assume that the highest stress in the model is going to lead to the lowest life. We have a large number of examples where cracks did not start from the high stress location, and this is because FEA stresses are only one part of the story. Another part is your loading. So we can't rely on the FEA stresses alone to give our fatigue life. Let's look at the very interesting case study from Hyundai Motor Company. The analysis was based on a steering knuckle. The benchmark was to investigate the effect of an overload as if the vehicle had hit a curb. There were 3 scenarios investigated. The first was essentially a constant amplitude, low-level load with a 0 mean stress. FESafe predicted the location of cracking at the top of the bolt holes, and this is where the part failed during test. The second scenario was to increase the constant amplitude and the mean to represent the load applied to that upper portion of the knuckle when there is a curb strike. Again, as you would probably expect, FESafe predicted the failure location at the top of the bolt holes. This is also verified in testing. So the third analysis was used to combine the first 2 scenarios, an overload followed by a constant amplitude load, as you might experience on the road yourself if you have a curb strike and then go back to normal everyday usage. Based on the first 2 results, it would seem logical to predict the same failure location. However, this was not the case. The failure location, as identified by FESafe, shifted significantly onto the arm of the component, and again this was validated by the testing. This shows quite clearly that the sequencing of loads can have a dramatic effect on the failure location, an effect impossible to incorporate except by using sophisticated fatigue analysis software. And now, we can see that the sequencing of loads can also have a dramatic effect on the failure location. Another part of the story is an intelligent software also allows us to account for the complex manufacturing effects that we use to create our engineering designs, such as stamping and forming. This case study by Ford is a fatigue assessment study of an oil pan, taking into account the forming process in the manufacturing step. The FESafe result on the left excluded the residual stresses from the manufacturing in the stamping plant, and the FESafe results on the right included those residual stresses caused by that stamping process. Taking the manufacturing effects into account not only identified new fatigue hotspots, but also reduced the life at the original hotspot by a factor of 30. That means that a component you thought was going to last 15 years only lasts 6 months, and you're unaware if your analysis doesn't include those effects. And we have now seen that manufacturing effects are also required to calculate accurate fatigue life conditions. With these case studies, we want to show you why you need to use an intelligent fatigue software in order to get fatigue analysis right. We have seen that FEA stresses are only one part of the story and that loadings, loading sequences, and manufacturing effects are other important elements that need to be considered. And FESafe will do all these things for you. FESafe is an intelligent software. It is unique because of the quality of algorithms we use. Its level of accuracy is only possible because of the advanced fatigue algorithms at its core. So an intelligent fatigue analysis software suite, such as FESafe, enables you to do all of these things listed in this slide. But in order to do these things effectively, it's essential that first and foremost your fatigue analysis software gives you accurate results, because only accurate results are meaningful, and as we've seen, getting the wrong result is worse than not doing a fatigue analysis at all. So the next question is, why FESafe? Isn't all fatigue software the same? This is a common question that we're asked, and at first glance you might say yes, but in reality it's not. Designing a component on the back of an inaccurate fatigue analysis, where we've not accounted for every condition, can have dangerous consequences. It could predict false fatigue hotspots or miss hotspots altogether. To avoid this, you need a suite of fatigue software that you can trust to identify accurate fatigue hotspots and give you accurate fatigue life. FESafe is an advanced suite of software with modern methods of multi-axial, strain-based fatigue at its core. It was the first commercial software to implement these cutting-edge methods and has been constantly developed over the past 20 years. As a result of this focus, our customers have the peace of mind that they are using the suite of software that they can trust to give them the right answers. FESafe gives excellent correlation with test results. The first example here is from Ford. It's an analysis of a welded joint, and the welds are said to be one of the most difficult areas when it comes to predicting fatigue life. As this slide shows, Ford was able to predict the fatigue life of this component remarkably well using Verity and FESafe. Only 0.83 repeats of the proving ground test were encountered before this suspension link started cracking at the weld, and Verity and FESafe predicted 0.81 repeats. The second example is a ball bearing from Schaeffler. This was a very complex contact problem, and FESafe automatically detects whether there's surface contact and switches to a more complex triaxial analysis. As you can see here, the FESafe life prediction was again extremely close to the test results. The third example is from Eaton Automotive. It shows an analysis of a single spring isolator in Eaton's twin vortices supercharger. When the spring is in operation, there's a very complex multi-axial stress state in the coil, and there are high residual stresses because of the forming process. This is also a case where the cracks don't start from the point of maximum stress, and FESafe predicted an astonishingly close fatigue life to the test results. You can see that these references come from our FESafe user group meetings over the years, and these are accessible to you if you'd like to read through these case studies. Please contact your FESafe support through your Simulia CSE office. And here's what some of our customers say about FESafe. You'll see from the highlighted points why our customers trust FESafe. It's because they have confidence in our team's fatigue knowledge and experience. They say they have chosen us because we have a very knowledgeable support team, the best support and solutions. We have in-depth fatigue knowledge, and because of the accuracy of FESafe. They say it's very fast, very solid, and very easy to use, and it has unique features. Triumph is the largest British motorcycle manufacturer, producing around 50,000 motorcycles a year. They chose to work with us to adopt the most advanced methods of fatigue analysis currently available. So back to our question, isn't all fatigue software the same? Designing a component on the back of an inaccurate fatigue analysis where we have not accounted for every condition can have dangerous consequences. It could predict false fatigue hotspots or miss hotspots altogether. To avoid this, you need a suite of fatigue software that you can trust to identify accurate fatigue hotspots and give you accurate fatigue life. FE-Safe development began over 20 years ago, and our continuous goal has been to develop the most technically advanced and most comprehensive and accurate fatigue software on the market. So let's look first at comprehensive. FE-Safe is comprehensive, and you can trust that it will handle any fatigue scenario. All the features you see here are included in the standard version of FE-Safe, and I'll let you read through them at your leisure. By establishing partnerships with well-known experts in their specialist field, we are also able to offer advanced and unique capabilities in addition to the standard metal fatigue analysis in FE-Safe. These partnerships have allowed us to offer you cutting-edge technologies as add-on modules to FE-Safe. With the Battelle Institute in Columbus, Ohio, we developed the weld fatigue module of Verity in FE-Safe. Verity is the original patented Battelle structural stress method for welded joints and offers a level of validation that no other structural stress method can match. With Amec Foster Wheeler, we have developed FE-Safe TurboLife for creep fatigue and thermomechanical fatigue calculations. With Endurica, we have developed FE-Safe Rubber for the fatigue analysis of elastomers. All of our modules are unique to FE-Safe. To learn more about any of these modules, we've run this webinar series, including sessions on each of these technologies. Please find links to the recording for any of these modules on the Simulia Learning community. You can see some of our new developments in the slide. The ones in gray are already completed and in FE-Safe, and the ones in blue are still currently in process. For instance, we're on a European committee looking at the fatigue of crankshafts, and this is looking at those effects of cold rolling and case hardening. So let's look at a couple of completed developments in more detail. We think the new material database in FE-Safe is possibly the largest commercial strain-based and stress-based fatigue database with more than 350 materials. It is certainly the most comprehensive data collection, having been fully validated, referenced, and reanalyzed by our staff metallurgist. It offers the unique ability of allowing users to search using US, European, Japanese, and Chinese standards within the same database. We also include high temperature, cast iron, and rubber material data with FE-Safe as well. This development shows how FE-Safe uses the information from the FE model intelligently. So for spot welds, we're already auto-detecting the number of sheets and their thickness. This means that the number of sheets and their thickness can vary in the model, and this can be auto-detected. We can also calculate default nugget size for spot welds if the user has specified them. And this results in the amount of input from the user being reduced. So that reduces the number of potential mistakes. This is an indication of the way FE-Safe will develop in the future, making much more of the information in the model used by FE-Safe and so reducing the number of user inputs. For some components, loading may be specified in the frequency domain, and these components may also exhibit resonances with particular frequencies. We didn't feel that the existing methods were accurate enough, so we developed a new PSD fatigue methodology. And our new method allows you to incorporate multiple block loading and multiple PSDs and cross spectra for superposition in those blocks. Phase information can be used if it's available, those cross spectra. And this new PSD fatigue method is computationally efficient and produces results very fast. The combination of complex loading and advanced fatigue analysis methods is completely unique to FESafe. It represents a major breakthrough in fatigue analysis technology for vibration conditions, and the methodology was presented at the ASME International Congress in November 2013. We have integrated FESafe into Simulia EyeSight, which allows you to use fatigue in your design automation process. We've also done the same thing in ANSYS Workbench. We can also develop tools for industry-specific applications, and this is an example. Here you have an Abacus CAE plugin developed by a Simulia CSE. The plugin designs the gear set based on handbook dimensioning, assigns materials, automatically meshes the model, and runs the Abacus analysis. Afterward, the job is automatically sent to FESafe and then seamlessly post-processed in Abacus Viewer. To the user, this provides for a single interface to run the design loop and simulation, including FEA fatigue analysis from start to finish. Now let's turn our attention to accuracy. Our customers report excellent correlation with test results, and we'll discuss why that is in the following slides. In this slide, I'll talk about the methods that are unique to FESafe and contribute to the accuracy of the fatigue analysis. Let's consider the first cube. We consider the initiation of the crack. For most metals, cracks initiate on shear planes, resulting from a combination of shear and normal strains. For complex loading, FESafe may have to search around to find the orientation of the crack plane, and this is called critical plane searching. The damage mechanism includes plastic strain, and so FESafe automatically uses a cyclic plasticity model when working from elastic FEA. FESafe is unique in the methods it uses to combine elastic plastic shear and normal strains. The crack initiation phase ends when the crack starts propagating in a direction normal to the loading. FESafe can check subsurface stresses to see if the crack will propagate or not, and this uses critical distance methods. And critical distance methods are unique to FESafe. For further information on critical distance methodology, please refer to this book, Theory of Critical Distances by Professor David Taylor of Trinity College, Dublin. Looking at the second cube, for some stress conditions, the crack initiation plane is shown here. Again, the mechanism is a combination of shear and normal strains, and again for complex loading, FESafe will determine if there's a need to search around many orientations of this critical plane. Looking at the third cube, most metals crack on shear planes, but cast metals crack on principal planes. FESafe makes the selection automatically in a model like this. The analysis process is repeated for each node in the model. Some of the other fatigue codes do not consider combinations of shear and normal strains. The methods used in FESafe are unique to FESafe and contribute to the accuracy of the fatigue analysis. This method is computationally intensive, so we have put a lot of work into making the code go fast. And we've written FESafe so that it makes intelligent decisions about which methods to apply and whether it needs to do a critical plane search, for instance. Some of our competitors will tell you that accuracy is not possible or necessary, but we have shown that FESafe is an accurate code and why accuracy is vital. First of all, accurate fatigue life results allow you to find the correct fatigue hotspot and to optimize your design for fatigue, and to give you increased confidence that your design will be right the first time. If you're working with assumptions and approximations, then the answer is going to be unreliable. You're not going to know if the answer is right or wrong, and if it's wrong, how much the answer is wrong by. You're not going to have confidence in your method, and you're not going to have confidence in your results or your component. That seems to us to be a complete waste of time and money. So here is our question. Why do your fatigue analysis wrong when it's possible to do it right? One more example before we leave the topic of accuracy is this helicopter rotor hub. These parts are subject to very complex loads from drag, bending, and axial forces. Yet FESafe can take into account this multi-axial stress state and still accurately predict fatigue life. The conclusions from this analysis were that conventional uniaxial fatigue methods would simply not be able to cope with this level of complex loading, and the multi-axial stress states in the component and testing to all flight conditions would be impossible. Hence, the new way to analyze these fatigue loadings is to use FESafe. FESafe will take into account the complex duty and loading cycles and predict the fatigue lives that are extremely close to real-life usage, just like they did in this example. We weren't involved in this case study at all until it was submitted to our FESafe user group meeting, and the correlation was excellent. Now let's look at the speed of analysis. Parallel processing and distributed processing have increased FESafe speed by leaps and bounds in recent releases. Parallel processing automatically runs over multiple cores on a machine if they're available, and FESafe supports multiple cores on a single machine at no additional cost. With distributed processing, scalability of the speed is linear, as the nodal calculations are distributed to your cluster nodes or workstation seamlessly. Let's see analysis speed examples from a few of our customers. On the left bottom of the slide, you can see the hardware and operating system of the test system we used for all of these studies. On the right-hand side, you can see model and loading conditions. And this is the supercharger spring example from Eaton Automotive that we looked at earlier. It is a very complex job containing results from two FEA solutions, and with complex superposition loading, making a virtual proving ground test, FESafe solved this problem in 19 hours. And this example is a wind turbine hub analysis. It's a fairly large model, again with complex loading, where each of the blocks represents different wind conditions the system might endure over time. FESafe solved this problem in 2.5 hours. And this example analysis is from a leading automotive OEM, and it's a full car body analysis of 27,000 spot welds using the new simplified spot weld method in Verity and FESafe. And again, a complex load duty cycle from the proving ground. FESafe completed this analysis in just 12 hours. And our final example analysis is from Cummins. It's a large engine block. With FESafe 6.4, our test system solved this very challenging analysis in 12 minutes. As you can see, the 2014 version of FESafe 6.4 is about 2.5 times faster than FESafe version 5.4 was. So we have seen that FESafe is comprehensive, accurate, and fast. But you may be wondering whether, as a user, you're forced to make a choice between speed and accuracy, which astonishingly other fatigue analysis software forces you to do. As we've demonstrated, compromising on accuracy is simply not an option, but neither do you want to spend hours setting up your analysis or running it for days and weeks. With FESafe, there's no trade-off between speed and accuracy. The analysis speeds shown in the previous slides are achievable with FESafe without any special settings and without compromising accuracy. This is not the case with some fatigue software where you're forced to make this impossible choice. So our question is, what is the use of a quick but incorrect answer? Given that FESafe is so comprehensive and able to handle very complex loading conditions and scenarios and analyses, you may be asking, do I need to be a fatigue expert in order to use it? No, you don't. Some fatigue software developers will tell you that you don't need to overcomplicate your analysis, that you don't need advanced packages for simple everyday analyses. But as we've demonstrated, real-life cases are rarely simple. The point here is that FESafe is intelligent software. Using it isn't overcomplicated or time-consuming, and all users will get that all-important accurate result regardless of the complexity of analysis. Not all fatigue software is the same. FESafe has default settings and an intuitive user interface that makes setting up your analysis quick and simple. FESafe will automatically select the most appropriate algorithm based on the selected material, which is its default setting, and standard analyses will be saved. Batch analyses are also easily set up to repeat analysis later on a different model or even with a different material. FESafe is not a black box because you can view the process and export detailed results. And if there's a temptation to think that such a complex suite of software as FESafe is overkill, let's think back to the fact that there is rarely a truly simple fatigue scenario. FESafe is so fast and easy to use, it integrates easily into your design process regardless of the complexity of your analysis. And you don't need to be a fatigue expert to use it. You'll never miss a fatigue hotspot again. So to conclude, we believe that FESafe brings you a level of expertise and confidence that you may not get from other fatigue codes. The license renewal rate is high, and this tells us that our customers have confidence in our accuracy and our quality of service. If you have questions, please feel free to contact your Simulia sales rep or reseller. If you don't already have a relationship with our Simulia offices, please feel free to reach out to our contacts shown here in your local geographical area. And thank you for your time. Goodbye.